Okay, what do you guys think? What's the best answer?
D.
All right. D. Let's check to see if that's the case. Increase the separation distance, the capacitance goes down. All right, so D. All right, give yourself 5 points. So that one, check to see what happens. So, okay, so if the electric field between the plates of a given capacitor is weakened, what happens to the capacitance of that capacitor, in essence? What happens to the capacitance of that capacitor? All right. So you weaken the electric field. Okay, the way you guys are looking at it is kind of cute. This goes down, this goes down, this goes down, and then you go, wait a minute, what do we do with this one? So does this go down? And then if that's the case, what happens to this? Or if this goes down, does this go up? And then this remains constant. Okay, and all of a sudden you get into that kind of confusion. Guys, the capacitance only depends on the area and the separation distance, right? Okay, so this thing is a physical thing. This is an energy storage device. How much charge it can store depends on the area. It depends on the separation distance. That's it. So it only depends on the area and the separation distance. It only depends on the geometry. So what that means is it's not going to change the capacitance. All right, so capacitance remains the same. Strength of the electric field has nothing to do with it. Okay, Ian, I'm going to give you 10 points despite the fact that I don't like your reasoning. Your reasoning has an underlying assumption. And your underlying assumption was the charge was constant. I think that's what you did. Okay, so the voltage goes up, the charge goes up, or voltage goes down, the charge goes down, provided that the capacitance remains the same. So I don't like
The electric field in parallel.
Okay, Ian, what'd you say?
The equation for the electric field, if that were to go down.
Okay, hold on. Okay, I'm ready now. Okay, so are we talking about this one? Or are we talking about this one?
Yeah.
Okay, equation number 4. Okay, tell me.
So
you're saying this goes down, this goes down.
The charge has to go down,
okay.
right?
All right, let's play that game. I kind of like your reasoning. This goes down, this goes down. If this goes down, this goes down. If this goes down, and if the charge goes down, you're thinking that this is going to remain constant. Okay, it's holy shit. That's not bad. Don't like it, but it's not bad. It's good mathematical reasoning. I just like conceptual reasoning. I like this so much. This one I like so much easier because it just depends on the geometry. But I see what you're thinking. Okay, so you made the assumption, obviously, that the capacitance has to be constant. That wasn't bad. I didn't see it that way, but I did learn something. All right, guys, take a break for 10. All right, guys, it was an unintentional long break.
Is really due to sheets of opposite charge facing each other on the metal surfaces. The field between the sheets is constant. The two sheets of opposite charge attract each other and hold each other in place. That's why a capacitor is such a useful device. If the voltage is held constant by a battery, the charge, and therefore the capacitance, changes inversely as the distance between the plates, and is proportional to the area of the plates.
Okay, so capacitor is a charge storage device. Okay, so there's going to be a constant electric field in between, which means that the energy is going to be stored in the form of voltage within the capacitor. If you drop a charge in it, it becomes energized. It's going to have potential energy. When you release the charge, potential energy is going to turn into the kinetic energy of that charge. So the question is this: what is the energy stored inside a capacitor? And we know that you can store energy inside a capacitor because as soon as you get 2 leads, when you charge up the plates by using 2 leads, you're going to end up getting a spark out of it. So that's going to be like light. So the amount of energy stored inside a capacitor can be represented by 2 formulas. All right. The amount of energy stored inside a capacitor can be represented by 2 formulas. All right, let's start using the formula sheet from time to time so you guys know where to find the formulas. Okay, so here's the capacitance formula. All right, so we covered this, and what else? And that's as far as we got. Okay, so we'll move up. Okay, so the energy stored in a capacitor is going to be represented by two formulas. Let's focus on this. U represents the energy of a capacitor. All right, so this is one formula, and here's the second one. All right, so energy of a capacitor. All right, so energy stored in a capacitor. Okay, so U represents potential energy or the stored energy. Here's one formula. Here's the second one. Okay. Okay, guys, using those formulas, answer these questions. Okay, so whenever you're ready. Which one do you think is the best answer and why? All right, so you're doubling the capacitance of a capacitor, holding the charge constant. So what happens to the amount of charge stored in that capacitor? What do you think? Any suggestions?
Doubles.
Okay, so what the hell?
What is energy?
Yeah, hold on. So double the capacitance of a capacitor, holding the charge constant. Okay. All right. Okay, so how do you do something like this? You hold the charge constant and double the capacitance, right? So what happens to the amount of energy stored inside the capacitor? That's what it means. All right. So double the capacitance. This is going to go up. This is constant. If this goes up, what happens to the amount of energy inside the stored energy inside the capacitor has to go down. All right. So which means that the best answer is going to be A. So it's going to decrease to 1/2 if that's the case. Okay. Who asked that question? What's energy?
Me, Ian.
Ian, what's energy?
I don't know.
Okay. Ian, did you miss that lecture?
Must have.
Okay. All right. So what's energy? Energy is the capacity to do work, right? Okay. So what does that mean? Okay. So what that means is it's the energy to the capacity to do work. That's what it means. And what's the meaning of that? The meaning of that is when you place a charge into a field like this, all right, positive charge, it's the capacity of the electric field acting on the charge to generate this force that's going to be able to move this charge from this plate to that plate. Okay, so that's the amount of energy that could potentially be transferred. So which means that more energy is stored in it, larger the strength of the electric field will be, the larger the force is going to be, the faster the charges will move. Okay, so that's the meaning of it in essence. So more energy you can store in a capacitor, the faster the charges will move and larger the current is going to be, which means that stronger the flash is going to be. All right, so amount of energy stored is going to give you the amount of force that you can generate in order to move these charges around. All right, Ian, give yourself 5 points for that question. All right, so doubling the voltage across a given capacitor cause the energy stored in that capacitor to, so if you double the voltage across a given capacitor, so what happens to the energy stored in that capacitor when you double the voltage?
Triple.
Say again.
They quadruple the voltage. Or sorry, the energy.
All right, so you double the voltage, so what happens to the energy? All right, let's take a look. So in this case, we're doubling the voltage. All right, so double the voltage. Obviously, the energy is going to go up, right? The amount of energy stored in it is going to go up. So don't forget that when you double it, you have to square it too. So this is going to go up by 4. All right, so if that's the case, I'm going to give you 5 points. Yeah, so it's going to go up by 4. You end up quadrupling.
What about the 1/2? Sorry.
All right, no, you don't need to apologize. What about the 1/2?
Yeah, because like, don't you like, because like, if you, because doesn't the
Bum,
one half
bum,
also,
bum, 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 bum.
doesn't one half also like kind of cuts out the 4 away into another half? Sorry.
Okay. Is this a yes or no question?
Yeah, I mean, I
Okay,
guess.
if this is a no, yes or no question, the answer is no. Okay, so move forward.
Okay.
Or do you want like an in-depth explanation?
Yes, please.
All right. Boom. Okay, so this. Okay, hold on. This squared, right? This is gonna. All right. What the hell am I doing? Okay, so this is which one? Are we looking at this one or the previous one? I forgot. Okay, you're
yeah, that
doing
one.
this one, right? So you double the voltage across the given capacitor, cause the energy. Okay, so you just double the voltage, and then what happens? Okay, so joke aside. All right, so when you double the voltage, what happens? All right, so here's the original. All right, so what I'm going to do is I'm going to double the voltage and then you square this. Okay, so now what happened? Now this 2 squared is going to be 4, right? So I'm going to turn it into red and then leave it in red because I like red. And then the rest of the expression is going to look like this. Do you see that? So this expression that you're looking at, this expression was the original. Capacitor is connected to a battery, it becomes fully charged, it's disconnected from a battery, so the net charge is going to be constant, so increase the separation distance. So what happens to the energy stored in that capacitor? Okay, so let's play with this. Okay, so the charge is going to be constant. This is charge. Increase the separation distance. So which means that capacitance is going to go down. If the capacitance goes down, what happens to the energy stored in that capacitor? It's going to go up, right? All right, so that should be the best answer. It should go up. So B is the best answer. Okay, somebody made a conceptual argument regarding this. Who made a conceptual argument?
That was me.
Okay, Nathan, what was your argument?
My argument was that with the charge constant, when you actually physically move the plates, you're putting work on the capacitor, so you're adding energy.
Very good. I'm going to give you 10 points for that explanation. You're doing work against the conservative force, which means that the amount of work that you do is going to go into the potential energy of the capacitor. Okay, so notice that that degree of conceptual understanding does not require any formulas. You can kind of arrive at the same conclusion by putting things conceptually, putting things together conceptually. All right, so somebody's having a heart attack. If that's the case, they use a defibrillator. The whole idea is to reset the heart. So they pump in about 20 amps of current into the chest cavity while hoping that at least an amp of current is going to reach the heart and stop it for a fraction of a second, like a thousandth of a second, just long enough to restart it so that the heart could regain its natural rhythm. All right, so let's turn this into a math problem.
As soon as scientists